Hello everyone. My name is Gabriel Hon, if you don't know me already. And so we're going to be doing a mechanical presentation today as part of our FRC crash course series.
Here's a quick introduction. It'll cover topics like tools, parts, motors, and torque.
All right, so tools. Once you get into FRC, you're going to see a bunch of tools, and it's important to know how to use each of them. So you can basically categorize tools into both hand tools and power tools. Also, there's an echo. I don't know if
That's trend.
Oh, I'm sorry. My bad.
it's okay. All right, so the first tool that I have on the list is the hacksaw. So that's the one on the top right corner. Basically, the hacksaw is like a blade, and you use it to cut metal, like aluminum. You can also cut other materials like plastic or wood. You have your hammer, which is pretty self-explanatory, right? You hit stuff with it. If you have like a nail or something, or some piece that you need to kind of shove into place, you can use a hammer. Screwdrivers for screws. And wrenches, you have different types of wrenches. So you have your combination wrench, which is that one with two different sides. And then you have your Allen wrench, which is the one on the bottom right. That one is for if you have like, let's say a button screw, right? Usually you would use an Allen wrench. And then you have your ratchet wrench, which is basically a wrench that can only, it bolts in one direction and it freely spins in the other, right? Then you have your power tools. I think most of you guys know what a drill is, right? You can use it to screw stuff in or to drill holes. A drill press is basically, it's pretty similar to a drill. It's just like it's mounted so that you can, it's basically more stable. So that way you can pull down the drill, and so that way it's more accurate and you can drill through stuff in a certain position or whatever. You have your miter saw, which is the big yellow one in the middle. That one's used for cutting wood. You can probably also cut metal with it, but it's usually used for cutting angles. It's pretty accurate with that. Your circular saw, which is kind of like a mini handheld version of the bigger one, and that's also used to cut wood. You have a sander, which is used to sand things, and your jigsaw, which is on the bottom left. That one's usually used to cut curves or any cool shapes in wood. All right, so you have a bunch of different types of screws and nuts. So we'll go over some of the main ones. You only need to know the boxed ones. Those are the ones that we use mostly in FRC. So you have your hex nut, which is just your normal nut, right? And you have the nylon version of that, which is basically has a little piece of plastic that prevents it from sliding out through friction. So it kind of locks in there. From your drive type, you have your normal Phillips drive type, which is probably what you guys mostly know or use. And you have a combination one, which is a combination of Phillips and slotted. Then you have your socketed or hex one, which is used with the, what I said earlier, the Allen keys. And then the different head styles, you can have rounded, you can have a hex, socketed cap, and also button. Button, I think we use a lot in our elevator, and that's also kind of usually an Allen.
Okay, so screws and nuts. Wood screws, they are used for wood. They're heavy. They have like heavy coarse threads. They cut into the wood and they hold the screw against it. And machine screws, they're like most bolts. They have a constant diameter across the entire thread length. Thread cutting machine screws, they cut their own threads. Sheet metal screws, they're used to hold sheet metal parts together. Don't use wood screws for this since the thread is not the right type. Self-drilling SMS screws, they drill their own holes and tap their own threads. Hex bolts have a heavy hexagon extrusion on the top. They're pretty common in FRC. Carriage bolts are tightened by tightening the nut. They're not that common, and lag bolts are used for fastening metal to wood. Again, they're not that common. Screw sizes. This is a chart of screw sizes most commonly used in FRC. As you can see, the thread diameter increases as you go up in size. These sizes are in metric, and they're referred to just by their size numbers. This isn't actually in the chart, but customary screw sizes are also used. They're classified based on their thread diameter and thread pitch. For example, a commonly used screw size is quarter 20 screw. This means that the thread has a quarter-inch diameter and there are 20 threads per inch. So if somebody asked you for like a quarter 22-inch screw, that means the screw is a quarter inch wide, has 20 threads per inch, and is 2 inches long.
All right, so torque versus speed. So I think most of you guys know what speed is. It refers to how fast something is moving. Torque is a little bit more tricky. It's basically the twisting force that causes rotation. So if you have a motor, how fast the motor is spinning is the speed, and how much force it's able to put into rotation is the torque. And so usually your motor is going to have speed and torque, and it's good to have a balance between the two. So you can measure torque or calculate torque by doing radius times force. That's just a generic formula. All right, so on the right side, we see a motor graph. So each motor is going to have a slightly different graph, but this one in particular is, it has that particular curve. And if you look at the two dots that we drew out, so the one on the right side, if you look at where it's positioned, you can see that it has a really high RPM. So it's at about 14,000 RPM. But if you look at the torque line, which is the yellow line, the torque goes to 0 as the speed increases. So that is called the free load. So basically, if you have a motor running with no load on it, then it just spins as fast as possible. So it's called free load. So your speed is the highest at that point. If you put a lot of torque on it and so much that the motor stops moving or turning, then your speed goes to 0, but your torque is at the maximum, which is, in this case, 0.36. And so usually it's good to be somewhere in between. So that way you're able to get both speed and torque.
Okay, types of motors. There are two types of DC motors, brushed and brushless. There are AC motors as well, but they're not using FRC since we use batteries to power stuff. The difference between brushed and brushless motors is their method of commutation. Brushed motors use these brushes here, those little red things, to transfer current between the coils, which shifts the magnetic field between the motors so that the shaft can spin. However, brushless motors have a small microchip that does this. Brushed motors are both cheap and easy to build. However, they're also easy to control. However, since the brush makes contact with the commutator at high speeds, its efficiency is inherently limited and the motor requires periodic maintenance. Brushless motors are a lot more expensive than brush motors and they're harder to control. They require an ESC to control them, which also adds the weight and the setup cost. However, they're more efficient and they don't require any maintenance unless something goes wrong.
All right, so there are a bunch of different types of motors that we use commonly in FRC. These are some of the ones listed are most common. And so first of all, you have brushed and brushless motors, which Pratik just went over. And so as you can see, brushed motors are usually running around 70 to 80% efficiency, while brushless ones are at 85 to 90% efficiency. So you have the first motor we have is the Redline motor. So this is a really commonly used motor, usually used for manipulation. So if you're manipulating items like creating a shooter or something, you would probably use this one. It has a pretty high RPM. It runs at around 20,000 RPM without any load. And so, yeah, the next one is some people I've seen on YouTube make insane gear trains with like a Google to 1 gear ratio, but that's probably not as practical. So the different types of gears include spur gears, which is just the normal one, bevel gears, which is on the bottom right, and then you have worm and internal gears as well. Belts and chains are pretty much for the similar purpose as gears. You just use them to connect gears at a distance. And so the one on the left is a belt. Usually we use that for like the drivetrain or something. And then the one on the right is a chain. We use that for our elevator.
Okay, gearboxes. There are many gearboxes using FRC, and there are lots of gear types within them. They cover a wide variety of tasks like driving, power shooters, /manipulators, elevators, etc. Inside these gearboxes, you can find planetary gear sets, worm gears, spur gears, and bevel gears. And you can judge what type of gears are in each gearbox by looking at the direction the shaft comes out of the housing relative to the motor shaft. So, for example, if this shaft were to come out here, you could probably you could assume that inside the gearbox is either a worm gear or a bevel gear. While most gearboxes have a fixed ratio, some gearboxes called shifters, they act like car transmissions and allow you to change ratios as the motor is running. However, they're pretty limited. They only have about 2 speeds compared to modern transmissions, which have about 10 speeds.
All right, so in FRC, we use a bunch of different types of wheels. So I've listed the most common ones here. So compliance wheels are able to manipulate items because they're kind of squishy. They're made of rubber usually, and so they're good for manipulating items because if your items change shape, then it will also be able to ignore the variations in them. So they're usually good for intakes or shooters or something like that. You have your standard wheels, which are a bit harder. They're usually made from rubber or plastic, and they can be smaller, bigger, or harder or softer depending on your needs. Usually we use those for something like a robot wheel, so the robot driving system. Omni wheels are kind of cool. They can move in the X and Y direction. So you don't need to, if you have them on the drivetrain, then you don't need to turn. You can just drive in whatever direction you want. Then you have mecanum wheels, which are used to push items in different directions. Those can also be used in the drivetrain and create you can drive in many different directions. And so, yeah. So Omni wheels and mecanum wheels can be used on the drivetrain or in different mechanisms. I think last year we used mecanum wheels as our intake, I think.
Here's a quick video of an Omniwheel drivetrain. They aren't that common in FRC, but they can be pretty useful at times since they can move in any direction without turning. Oh yeah, also you guys don't really need to hear the sound.
Yeah, so you can just see the robot moving in both the X and Y direction. They're not as common in FRC because you're probably going to have less power because your wheels are shaped differently or pointed in a different direction.
And they have rollers on them as well, which makes them easy to push around.
Yeah.
And they're extremely complex to build, so we don't use them much.
But they're kind of cool.
Yeah, if I can cut in for a quick second. Yeah,
Go
that's
ahead.
don't use is mostly like complexity, or obviously like if you have a drivetrain that looks like a square, then that also kind of limits you as to what you can put for electrical. So yeah, that's why they're not as common.
But some teams use them.
Yeah.
Okay, rotational and linear motion. There are 2 types of motion in FRC, linear and rotational motion. Linear motion is obviously an object moving in a straight line, like this GIF of a piston here. It's achieved using pneumatics, belts, chains, pulleys, and shooters. It can also be achieved through hydraulics, but I don't think hydraulics are allowed in FRC. Rotational motions, you're pretty familiar with it. It's an object moving in a circle like this. Some examples are motors and wheels.
All right, so mechanical design calculators, this is basically just some kind of spreadsheet that has information about different configurations of drivetrains or whatever motors you have. So as you can see, this particular one's using a sim motor, and it will tell you the amount of pushing power and also the speeds that you will get by using that certain configuration. So that's pretty useful if you're designing whatever mechanism beforehand, just to know. All right, so now we're going to go more into the robot and the robot. So we split it up into 2 different parts. So you have your robot base, which is the frame, drivetrain, and wheels. And then you have your manipulators, which is basically scoring points for you. It's your arms, elevators, intakes, shooters, whatever you have. Right. So the first one is robot base. So the robot base can be split into the frame or chassis and then the drivetrain. So the frame is basically, if you look on the right picture, it's the metal pieces that are holding the robot together. So everything that you're going to build is going to mount onto that frame. So you first build the frame and you can mount everything on there later. So the drivetrain is the moving parts of the robot base. And so it consists of the wheels, which are usually standard wheels. And then you have your motors, which is either a Sim motor, Falcon motor, or Neo motor. And the gearbox that you're normally going to use is a Tough Box or Evo gearbox. And so the motors are going to power the middle gear, as you can see in the picture. And so belts are going to connect the other two wheels so that all 6 wheels can move forward or move in whichever direction you want. And so the goals of the robot base is to move quickly, efficiently, and precisely. So it also should have enough power to push other robots if you're playing defense and you want to make sure that other robots can't get where they need to be. And if another robot is pushing you, you can push them away and move on to wherever you need to come. And you also want to make sure that it has a low center of gravity, so that way your robot doesn't tip over, because if your robot tips over, then you can't really go run in there and help it. So it's for stability.
And also, I'd like to add that the drivetrain comes it comes with the kit of parts. It comes from first. We just cut the parts to fit them to the shape we need, and we just bolt them together. We usually remove these churros from the middle.
Yep.
And now arms. There are a couple of arm types in FRC. There are single and double jointed arms. Triple jointed arms exist, but they're complex and not really that rare, or not really that common. Arms are used to like lift, dump, stack, throw, and fling objects. Most arms are high speed, low torque because they're usually used to lift game pieces which aren't that heavy. As a result, they need to be lightweight and balanced to prevent vibrations or stalled motors. Not many parts are needed for an arm depending on the type you're building. Often they have a grabber or some other manipulator on the end to move other objects. An optimization is required because there needs to be a perfect balance between force and speed to help give your team the most points possible. And motors used for arms are Neo's Falcon 500s and Sims, the same motors used for drivetrains.
All right, so shooters. So if you have whatever balls, like last year we had dodgeballs on the field, then you're probably going to have some kind of shooter. So shooters are using or shooting usually balls to score points. So there are different types of shooters. The most simple one to make is probably a linear shooter. So that's the one on the top right. It's pretty easy and it's pretty accurate. It's just 2 wheels spinning, pushing the ball forward. You can also have more wheels. You can have like 4 wheels. But those are usually just shooting straight and they're pretty simple. Arc shooters is the one in the middle. So that one has just 1 wheel or 1 motor spinning it. So that way you can add backspin to the ball. And backspin is good because it moves the ball up as it flies and it's more stable, whereas forward spin will move the ball down. And so the last one is the catapult or launcher. So this one is a little bit more difficult to make, and it's also more limited to where it's shooting, where you can shoot, because the amount of force that you have to calculate to actually shoot in and make it in. And so this is good because the catapult will not it will not be affected by variations in the objects. So if the ball is a little bit deformed or smaller, then your linear shooter might have a hard time getting as much grip on the ball as normal, whereas the catapult will just shoot the ball anyways. And so the motors used for these kind of shooters are usually Redlines and mini sims, and maybe snowblowers for articulation.
Okay, elevators. Elevators are used to lift the robot. Robots are a little under 150 pounds, so the elevator has to be pretty strong. It can be used to lift other things like actuators or game pieces, in which case the elevator doesn't have to be as robust. And there are many types of elevators, the most common being single and double stage. The only difference between the two is the number of sections. For example, the picture in the middle is a 3-stage elevator since there are 3 sections being lifted, the red one, the blue one, and the white one. Elevators use wheels and gears to move, like this picture or this one. Some elevators may use pneumatics, but this is pretty rare. Motors used for elevators include Neo's Falcon 500s and Sims. For the frame materials, the rectangular part, materials such as Rev Robotics elevator extrusion or 80/20 1-inch beams can be used. And most elevators have large torque and low speed, though this can be controlled by changing the motor and the gearbox if it has one.
All right.
Thank you. Do you have any questions? Oh, hi, Nathan.
Well, it doesn't look like there's any questions, so I guess we'll just go ahead and end it here. Thank you everyone for coming. That was our introduction to mechanical, like FRC. That's part of the FRC Crash Course series. We'll be having another one at 12 or a bit after on strategy. So go ahead and check that one out, as well as we'll be discussing a bit more in depth as to some parts of the robot and how they interact with each other on the field.
Bye, guys. Wait, actually, Fernand, do you want me to stay after?
No, there's no need.
Okay.